Hi everyone, and welcome back. Brahim Siddiqui with you. This is a continuation on the series of videos that I'm presenting and trying to detail the new approach that was published in a paper to revolutionize the project control using control theory. So from last video, I start talking about very interesting concept that was developed in the control system. And one of these two important parameters was the zeta or xi, and we said this is risk damping ratio. And another important characteristic, which is the angular risk velocity, or basically we can say this is a risk frequency. And also we define the governing equation for the project control in general based on these two parameters. And the governing equation of the dynamic system, so the budget dynamic system, defined as the acceleration of the distortion plus 2 risk damping time the risk frequency omega n time the velocity or the speed of the distortion plus omega n square distortion with respect to time. And we said as a general form, it will equal to gamma time omega n time u of t, where u of t is the desired distortion. And we said that we can model this ut. It can be constant, it can be sinusoidal, it can be polynomial, it can be stochastic, it can be anything. And but we didn't explain or emphasize the role and the benefit of these two parameters. Also, we found that Xi or risk damping ratio was based on the variable cost, initial variable cost, the planned variable cost. And the variable cost, we said, is a direct cost over 2, the square root of your budget, x0, time f0, which is your fixed cost. And we know that x0 is your direct cost, variable cost, plus f0, which is fixed cost or indirect cost. So, and then we said variable cost or direct cost are almost the same fixed cost is indirect cost is almost the same. And also we define omega n as the omega n square, sorry, is the risk frequency, which is the budget over fixed cost. And also we define omega n as a 2 pi frequency. And that's why we call it risk frequency, because of this. And also we said that the distortion, it will have different expression based on the risk damping ratio. So if the risk damping ratio between if zeta between 0 to 1, so we said that this is under damp. If it is equal to 1, this is over damp, I believe. So let's check here. Yeah, it's here. So if it is 1, critical damped, end damped, and over damped. Okay, so if it is 1, so we say critical damped, and equals 0 end damped, and over 1 over damped. So I gave you, I believe, a brief explanation, but I didn't detail it in a concrete example. So that's why today I'm going to show a concrete example, and then we define the parameter design specification of the performance of this simulation that you see, the graph that you see in front of you, which is the distortion risk response. Okay, so we can say that in control system, the distortion in control system, the risk damping or the zeta determines how quickly a system stabilizes after disturbance. For example, in this case, it looks like the budget system is disturbed. Maybe we don't have enough budget, or maybe the duration is too long, that will create troubles in terms of budgeting. So and this scenario, for example, this oscillation probably it comes because of low risk damping. So which means if risk damping is low, it means that the system is under damped. So that's why this scenario is between less than 1 and greater than 0. So which means it's under damped. So this scenario that you see in front of you is under damped. So which result in large oscillation. So you can see the graph is oscillating here. So large oscillation and high overshoot. Last time I mentioned about the overshoot, and I said this is what it means. So, and then it will be represented in percentage. We can say this is 20%, 10%. I mean, the higher overshoot, the more oscillation that you will have in your system. So the high overshoot before the, your project will settle. So this is the settling time, which will be the duration here. So it will settle somewhere in 20 weeks. And before that, you can see all this oscillation because of um, the risk damping ratio. Okay, so what it means? So in project management or project risks, risk damping can represent the degree of control or risk mitigation applied to stabilize project input or project budget and duration. So by controlling this parameter, the risk damping, so we may change the nature of the risk response. So what it means? Um, so let's. So what it means that if we have high risk, high risk, it's equivalent to low zeta, low risk damping. If we have low risk, it means high zeta. Okay, so but what it means in a project risk for this case, so we have high risk. Low zeta means we have insufficient control mechanism. We can say poor planning. We may have inadequate contingency. We may have weak feedback loops, and which all of this will lead to a large overshoot. Probably also we can add scope creep, maybe not sufficient budget, or maybe the duration is not realistic. So it could be a lot of things that the response on the this risk response of the distortion, it shows something like this. So this is for low risk damping. For high risk damping, which is low low risk. So let's delete this. Have enough space here. So for this one, so we can say that we have high risk damping and low risk. So, which means reflects robust risk management. It's an indication of robust risk management with strong control to minimize deviation from the plan, and quickly stabilize the project or activity budget and duration. So it also mean for this, if you have low risk damping, it means that you have high overshoot. If you have high risk damping, it means you have low overshoot. So you can tie this low overshoot with the low risk, high overshoot with high risk. So basically, managing the overshoot or controlling this overshoot, so you control the risk mitigation. You will have the ability to control the risk and to control your budget in general. Okay, so let's delete this. I would like to have some space here. Okay, and okay, so this is in a nutshell. And if I draw a graph, so this graph, let's say this is the risk damping, and this is the overshoot. So there is a mathematical expression of the overshoot, and then it is defined as 100 times exponential of minus pi c over square root of 1 minus xi squared. Okay, this is the expression. I did not demonstrate this, but probably next video I will show you how we come up to this mathematical expression. First, you can see that this is an exponential, and you see the negative sign. You know, if you have minus a, it means that it declines like this. No. So it means that it declines and then will vanish when time goes to 0, or the x-axis we go to the infinity. So it's declining, okay? And then it is based on C, and we can draw the graph. So if you say this is 1, so it will be something like this. No. Okay, so if I so it will be something. It's an exponential. So this is 100 exponential minus pi c over 1 minus c square. And as an example of, so what means this? So this it illustrates how the percentage of overshoot decreases. So when the overshoot decreases exponentially as the risk damping ratio increases. Okay, so when the risk damping increase, the overshoot decrease, as we explained it earlier. For example, if you have 10%, say 0.1, so this give you roughly 65%. Now, if you keep decreasing, let's say 40%, then it gives you certain overshoot. You just plug the 40% here, and then you get this overshoot. So and then the overshoot is high when the risk damping is low and indicating significant oscillation, like what you have here. So we can see that it's oscillating. So and the overshoot is the maximum. This is the first overshoot, and then we have another overshoot here. This is the second, and then you have here the third, and then keep declining until the settlement, until will be vanish basically. So so as the risk damping approach one, the overshoot drops to near zero, reflecting nearly critical damped. So which means that we are in a different mode or stage, and we said that if c equal 1, and this is critically damped, and we know how the curve will look like. So it will look like this, and so it's the system with the minimal or no overshoot here. So basically there is no overshoot here. So you can see now the importance of the risk damping, and keep in mind that the risk damping is defined by this expression. So which means if you change one of these variable cost or fixed costs or your budget, so you have to find the appropriate ingredient in order to get the best risk damping for your system. And also, I want to talk about the settling time. So you may ask why the duration stop here. Okay, why not here? So, and the reason is, so what we do is what the control system suggests is to create a criterion or a band. If I, let's say, band of, let's say, like here. So, and then I say this is, Okay, and duplicate, then will be somewhere here. So what it means, I will show you, just give me a second. So here we have um, from 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 the steady state. So this is the red line here is the steady state, and this is, we call that delta. And this delta, it could be between 2% to 5%. So this is a user input. So which means that when the curve, because the curve is declining, it's going to settle when it goes to the infinity. When the time goes to the infinity, it will settle to the steady state. So this dashed line, we call that the steady state. So which means this is your desired output. And but we cannot wait until it goes to the infinity here. So it has to stop. When it stops, when the curve is tangent to this criterion, to this 2%. So which means the curve stay within this range. So within this range. So, but we will stop when it reach when it touch the first criterion. And then we said, this is the settling time. This is the procedure, and this is the convention, if I can say, that was adopted by the control community. And then there is an expression for that, and this expression, mathematical expression for this duration. So they call it settling time, and the formulation, it's approximately minus log delta over the risk damping time omega n. So this is the mathematical formulation on how to determine or find the duration, the settling time when you have risk damping and angular frequency. Okay, so this is I give you example here. Is the same curve like the one that you see here, but we show you the data here. So given a duration of 20 weeks and given a budget of 12,000. Based on these two input only, we can decompose the budget into fixed cost and variable cost. And also, if we know these two, and we know the budget X, and this is a duration, so we can compute the risk damping, which is the Psi, the risk damping ratio. We can also compute omega n, which is the risk frequency. And if you know risk damping, then you will know the overshoot. So, and the estimated duration, it's almost, this is computed by the program, by the algorithm, which is approximately 20 weeks. So if the user put this budget and put put this duration and this budget, this is what he's going to get. So, which means a simulation here. This is a response to the budget of 12,000 and the duration of 12 weeks. Sorry, 20 weeks. And this is the response. This is the response that we get. And we get this design specification or performance. So based on this feedback, based on this information that we get from the risk response, then we have to do something. So now I know for sure that this budget system is not a good, I mean, it's not a good budget that can carry the execution of a particular activity. So, which means that we have to do something in order to make this smooth. So, which means we have to reduce the overshoot. Okay, and also based on what we learned from previous videos, so we define the transfer function. By the way, these curves, this response is obtained through the transfer function. And if you call that the transfer function, we define it as so we say GS equal distortion over US, which equal gamma times omega n square S square plus 2 omega risk damping time risk velocity S plus omega n square. And we made an assumption here that gamma equal 1. And then we said because the risk appetite sensitivity factor, historical risk appetite sensitivity factor equal the risk appetite sensitivity factor of this budget system, which is 20 weeks and $12,000. So we made this assumption just to keep things simple. And now I can, through this, when I put this budget and duration budget and cost budget into the system, it gives me this transfer function, which is this. And based on this transfer function, we did through the Laplace transform. And then we say this is US and GS, and this is the transfer function. And then we get the mathematical expression based on risk damping and risk frequency based on these two parameters. These two parameters, and this of course we do the inverse of the Laplace transform in order to get it in the time domain. And this is in time domain. This is in time domain. Okay, so you see now things become simple. You just need your budget and your duration. That's it. And then I will show you how we segregate or we decompose the budget in fixed cost and variable cost. I need some space here. So let's delete this. Okay. What I'm doing here. Aha. Okay. So let's delete this. Okay. So let's generate a mathematical formulation um, for the variable cost and fixed cost just by knowing only the duration and the budget. Okay. Okay. So from the this given formulation, so we know that duration equal minus logarithmic of delta over risk damping time angular risk velocity or risk frequency omega n, and we know also that the budget x0 equal f0 plus v0, where f is fixed cost and variable cost. Okay, so what we have only these two inputs, your budget in terms of cost and your budget in terms of duration. And the question is to find risk damping, omega n, variable cost, and fixed cost. So we have to find 4 parameters just by having these two. Okay, so we know also that V variable cost over fixed cost equal to risk damping omega n. And this is based on the governing equation. See, the governing equation is the framework of all what we are doing here. So we have, we can rewrite this, and then we can say that variable cost equal to omega n time f0. Okay, and we know that x0 equal f0 plus v0. So, and then we can say that x0 by substituting v0, so which become f0 1 minus, because here there is sign minus, 2 over the duration here. So we can say that omega n minus over duration. So we get this from this. And we substitute V0 into the this equation. So basically we know that x0 over f0, which is 1 minus 2 over d. And this is what? This is omega n squared. So which means we can find omega n is the square root of 1 minus 2 over duration. So basically, if you choose certain criterion band between 2% or 5%, and you know the duration, you get omega n. Okay, so you get the omega n. Now, what we can do here, or from the same expression here, we can say that f0 is x0 over 1 minus 2 over duration. So you have your budget, which is 12,000, and you have your duration, 20. So you get the first fixed cost. All right. So V0 in this case, we said is x0 minus f0. So which means V0 is x0 1 minus 1 over 1 minus 2 over duration. Because we substitute f0 here, and we have x0, so x0 will be a common factor, and we get v0 as a general, so which is minus x0 times 2 over duration divided by 1 minus 2 over duration. So you can get the value of fixed cost and variable cost just by providing total budget and duration. So total budget and duration, assuming delta equal 5%. So basically, you can further simplify, because when you take 0.05%, 5% of logarithmic, you get up. 0.02. You get approximately 4. So here we say 2%. So if this will give you approximately 4, and then if 5%, approximately you get 3. So which means you can simplify, you can replace logarithmic of delta by 4 or by 3. And we said that this based on the band and the criterion. Okay, so now we have an expression, mathematical expression of the variable cost and fixed cost just by plugging the budget and the budget for in terms of cost and in terms of duration. Now, once you know the what they call it, the variable cost and the fixed cost, so we can determine the risk damping, because we said that it is variable cost over 2 x0 times f0. So we can compute f0, and which is direct cost. It is found 8.63, and the variable cost is 3.37 thousand in terms of thousand here. So immediate response here based on this calculation. And what is the risk damping? Is 16.6, and the frequency is 1.78. How we come up? We come up with this formulation because we know everything, and omega n is the square root of x0 over f0. We know this, so we can get the omega n. Now, what is the overshoot? So the overshoot, we have the expression, and we say 100 times exponential minus pi c over square root of 1 minus c squared. So you know c, now you know the overshoot. How much? You can see it's 58, you can say about 59%, which is very, very high. So now it gives you an idea based on the budget that was given to you by a contractor or by the estimator group. Then this budget is not sufficient. I cannot say it's not sufficient, but it has the risk response. It doesn't appeal that this activity will be carried out in a good standing. So either way, if we want to maintain the budget, then we have to play on the indirect costs and the direct costs, on the fixed costs and variable costs. But also, which means that you may reduce your indirect costs and you increase your direct costs. Increasing the direct cost means increasing the labor, or in the indirect cost means remember also that C can be written as this is the rate, the unit price for the labor, for V time L, 2 time x0, the unit rate for the asset, time C. And this can be written over 2 like this, x0 and f l c. And this you can say A time L over C. L, which is the number of labor, and this the number of equipment, machinery, and all of this is a constant because the unit price for the variable cost is given. You know the total budget, you know the unit price for the fixed cost, for the indirect equivalent, of course. Then what is left? You have to play on the labor, and so basically you play on the resources. You see how easy it is to do an estimate just by knowing this control system tricks. It's very, very strong, and then we can reveal. I mean, we can detect more than that, but we go step by step. Okay. Now, what if someone will tell you, okay, since the overshoot is a critical output from the the simulation that we have done just now, why not reduce it? Well, I say, okay, so we can reduce it, but how much? So someone will say, okay, for now, for example, this has how much? 58, around 58.80%. So I want this to go um, like like this because I did for different different overshoot. So for example, this one. Uh, so we have the initial budget. We have the original risk damping and risk velocity and the original sigma, which is this is sigma means omega n. And the new risk damping and the new risk velocity, which is different, and the new sigma, which means a new transfer function. And this is the original, and now for 20%. Someone give you this based on risk mitigation and the based on discussion within the project team, they decided that okay, let's reduce the overshoot to 20%. And but when you reduce that, then there will be a cost. So you can see that the new budget increase and your fixed cost stay the same because someone will tell you, look, so we are renting, we are leasing this material or this equipment. It has a fixed rental, so we cannot change it. However, if you want to achieve 20% overshoot, then the only variable that you can play with is your labor. So you increase your labor means you increase the cost of your direct cost or your variable cost. And when you do the simulation, you can see now that the duration being decreased from 20 to 5 weeks. 5 weeks. So look at the original duration and look at the estimated duration. It's a huge decrease in terms of duration. Now, if someone want to reduce further, and we say this is how much 20, and here is sorry, this is 40. This is the original one. No, yeah. So the original was the original. Oh yeah, original was 58.8. Now someone say 40. You can see some oscillation, but it gives you only the duration be decrease, of course, but not like this one, not like this one. So, but also the cost, the new budget is 15,000, but here is 20.86,000. So you can see that by just changing the overshoot, you get the response and it gives you the settling time. Same thing here. If you want to go further, you reduce your overshoot, say 10%, and but it comes with the new budget. Now increase the budget. Basically, you increase the variable cost, increase the variable cost here, your labor, and then you maintain the equipment, and then you see the duration is only 3.4, and you can see here the overshoot been decreased. And here almost zero, so which means that the C it's almost zero. It will never reach zero, but 0 point something. And you can see it here. Risk damping is 0.826. And yeah, and look at the budget here is a increase, but look at the fixed cost didn't change. So the project team made the decision that we will not touch the fixed cost. However, we can play only on the variable cost, and the duration is only 2 weeks instead of 20 weeks. But this is the budget that you need to have in order to finalize this activity within 2 weeks. You see, and you have a new transfer function. Keep in mind that this is obtained through this transfer function, and then I showed you this last week and earlier. Okay, but now you may ask how we obtain because the user will suggest an overshoot value. So you see that we reduce it from 58.8 to 40%, and then blah blah until zero, until almost how much the last one, the new overshoot, almost 1%. So 1%. But when you change this, you are going to change the risk damping. When you change the risk damping, it means that you are changing the variable cost. You are changing the variable cost, and the budget and F0 will stay the same. So basically, this stay the same. However, the budget and the variable costs are going to change. They are going to change based on your overshoot. If you set an overshoot 40%, then you will have a new value. If you have a new value, but what is the relationship between them? And I showed you that the relationship here, there exists between the risk damping and the overshoot. It's a it's a decay exponential, and we have this expression. But I know the overshoot, but I don't know the risk damping. So we have to solve this equation. Okay. So what will be the expression? Okay. So we know that overshoot equal the overshoot equal 100 exponential minus pi c over 1 square root of 1 minus square. Then we can do like this: overshoot percent over 100 equal exponential minus pi 1 minus risk damping square. We have an exponential here. I guess the logarithmic will do a good job. So we get logarithmic of overshoot over 100, which equal minus pi c over 1 um, minus c squared, and then we take the square root. So we can say minus 1 over pi logarithmic overshoot over 100 equal c 1 minus c squared. Let's put this, we call it z. Okay, so we have z equal minus 1 pi logarithmic of the overshoot over 100. This will be a constant. This will be a constant because someone is giving you the overshoot, like what we suggest earlier. And what we'll get? We get z equal c over 1 minus c squared. So we have to solve for the risk damping. So which means that, but before that, let's, we can write this as square 1 minus square like this. And then we take equal 1 minus square. So we can do that, right? Then we solve. So it be z square minus z square risk damping square equal square here. So we can say, okay, z square minus z square minus equals 0. And we can take this in common. So we can say z square minus this z square plus 1 equals 0. This means that square equal z square over z square plus 1. So which means that is z square root of z square plus 1. Okay, then we can substitute the z in terms of OS, and then we get this equal minus 1 pi logarithmic of O overshoot over 100 over will be, so here we can say 1 pi. Before that, so we have 1 pi square time logarithmic overshoot over 100 square plus 1. Is that correct? And okay. And this is, I think I did a mistake here. It's not plus, it should be, I think I did a mistake. Okay, let's do it again. So here we get z square equal 1 minus square, yeah. And then after simplification, so I will get equal z square over 1 plus z square. And then I will say is square root of z square over 1 plus z square. Okay, so let's replace everything. We have 1 over pi logarithmic of OS over 100 over 1 plus 1 pi square logarithmic of OS over 100 square. Yeah. And we will have minus logarithmic of OS person over 100 over pi here, it is pi square plus logarithmic OS percent over 100 square. So which means that the expression will be minus logarithmic OS over 100 divided by the square root of pi square plus logarithmic of OS divided by hundreds, and all of these is a square. So this is the expression. So which means when you have OS here, so you have OS, the overshoot, you just plug a number here, and then you get the expression. One more thing that we can get the omega n. You remember that V0 over F0 equal 2 omega n, risk damping omega n. And we said that there is another way on how to get the omega n. Remember that x0 over f0 equal omega n square, and omega n square. And we can write this also as a 1 plus v0 over f0, because x0 is f0 plus v0. And we can say that omega n square is 1. So we substitute this here to see omega n. And we can say that omega n square minus 2 c omega n minus 1 equals 0. And this has a solution, which is, and you will find it's c plus minus 1 plus immediately. So if someone give you overshoot, You can calculate your risk damping. You plug your risk damping here, you get risk velocity. If you know the risk velocity, so you can write your governing equation, which is 2 times epsilon, the velocity or speed, plus omega n squared epsilon t equal something here. Okay, so hope that I did not confuse you, and you can see that you can do you can validate your estimate, your budget estimate based on the risk damping and the risk velocity or risk frequency, and you can make a decision whether to fix the variable cost or the fixed cost. What I have done here is just we fix the fixed cost or the indirect cost. So we can do the opposite. So we can say I am flexible with both of them, or I'm flexible with the risk. I'm flexible with the fixed cost, but I'm not flexible with variable cost. Or I am not flexible with the total budget. I cannot change my budget, but I am flexible to change both of them. I mean the variable cost and the fixed cost. And you can play with all of this formulation, and then you see the response you through the transfer function. And this response is going to tell you if whether your decision, your I mean, whatever you agree with your project team is realistic or not. Thank you very much, and please, if you like this video, subscribe and hit the button like. And if you have any comment, don't hesitate to write it down and let me know. Okay, see you next time.